Hi there, Mrs. Thompson here to talk to you about bonding. This is our new unit, going over Chapter 8 and Chapter 9. Please write down any questions that you have, and I'll answer them when I see you next. All right. Okay, so some vocabulary terms. First one, chemical bond. Now this is an attractive force. Remember that attractive forces are what pull things together. So it's an attractive force that holds atoms or it holds ions together and it binds them or forms a bond and it turns them into something new, which we call a compound. The reason why atoms do this is so that they can gain stability. They go from being higher energy to lower energy by either losing their valence electrons or gaining some valence electrons or even sharing valence electrons to be stable like noble gases who have 8 valence electrons, except for helium, who only has 2. Next word, chemical formula, and that's just a way to express which atoms are involved in a compound and how many of those atoms you have. You can tell how many atoms you have by looking at the number of capital letters in the formula. So for example, in this cute little joke, it says, "Hey girl, are you made of copper and tellurium? Because you are cute." You can tell cute, if it were a real chemical formula, it would have 2 elements in it because it has only 2 capital letters. Okay, here's some examples of chemical formulas, and we're just going to go ahead and count how many atoms of each type of element we have in each one of the 3 compounds. So here's the first one. We have a subscript of 2 after the H, which means we have 2 H's. H just stands for hydrogen, so 2 hydrogens. Then we have another capital letter, which is capital S, that stands for sulfur. And we have 1 sulfur. It doesn't have a subscript, but it's always an understood one. Then we have this 4 right here, and that's next to a capital letter for oxygen, O. And so we have 4 oxygens in that formula of what we call sulfuric acid. Our next chemical formula, C3H5 and then parentheses, NO2 with a 3 outside the parentheses, that's a little bit different because now we're dealing with parentheses. That kind of helps us to figure out what the formula looks like later, so the structure of the atom. For now, we're just going to learn how to use the parentheses. So let's start with this one. We have 3 carbons, 5 hydrogens. For the parentheses, what you would do is you would distribute that 3 to both of the atoms inside of the parentheses. So if we have 3 times an understood 1, that would be 3 nitrogens, and 3 times the subscript of 2, which would give me 6 oxygens. I'd like you to try the next one and see if you did it right. Okay, let's see how you did. So we have 3 magnesiums, and then we have some more parentheses, so we'll distribute the 2. That makes it 2 phosphorus and 8 oxygen. Okay, next we'll talk about electronegativity. Here it is. It's the ability of an atom to attract a bonding pair of electrons. Okay, so in our bonds, what's going on is electrons are being shared or they're being completely taken. So one gives and the other takes in a bond. And so electronegativity is how good an atom is at drawing in electrons. So how attractive it is. That's why you see this cute little cartoon of an atom holding a magnet drawing in some electrons. Atoms that have high ionization energies also have high electronegativities, and that's because in ionization energy, it's the energy required to remove an electron. Now, atoms that have a strong nucleus will hold on to its electrons better, and so it takes a lot of energy to remove it, and therefore they have a high ionization energy. For electronegativity, same thing. The stronger the atom is, the better it is at attracting electrons. Here's the trend. Okay, so what you'll notice here, if we look at the numerical values, now these are all measured values. Let's just go across period 4. So as we go across period 4, what you see is these numbers are increasing. For the most part, there are some dips, but mainly the electronegativity is increasing from left to right. Okay. The reason for that is because the nucleus is becoming stronger as more protons are being added. The other direction. So the reason why at the top these have a higher electronegativity is because the atoms have less shells at the top. And so the distance between the nucleus, what's attracting the electrons, and the electrons of another element is a lot smaller when there are less shells. And so the more shells I get, the further away the electron is, and so its ability to attract electrons becomes less and less. Okay, you're going to need to copy this table down as we talk about types of bonds. Not sure where a good spot is. Okay, so here is something that you should look familiar. It's where are the metals and the nonmetals on the periodic table. Okay. You have this staircase where the metalloids exist. And to the left you have the metals, to the right you have nonmetals. And then over here you have hydrogen, which is a nonmetal, hanging out with the metals. And that's because it has one valence electron. Alright, so what types of atoms usually get put into covalent bonds are just nonmetals. For example, H2O is made up of hydrogen and oxygen. It's a nonmetal plus a nonmetal that creates a covalent bond, usually. For ionic bonds, we take something that has a very low electronegativity and we add it to something with a very high electronegativity, a nonmetal, and you form an ionic bond, metal plus nonmetal. Here's that table of electronegativities again. And here's what we're going to do with it. You can determine the type of bond by more than just simply looking at what type of element it is. You can determine this by looking at the differences in electronegativity. And so what you would do is you would just take the higher electronegativity and subtract the lower one and figure out where that would fall into a range. And so let's make the range and then I'll show you some examples. Alright, so if we take 2 and subtract them and we come up with a difference of less than 0.5, that would give me something that is nonpolar covalent. That's because both have similar electronegativities and instead of one taking electrons and the other giving, they share the electrons. If they fall within a range of 0.5 to 1.7, we consider them polar covalent because they share them, but they share them unequally. And if it's greater than 1.7, that's ionic. One atom is so electronegative that it takes the electron completely away from the other. Okay, and you can find a table like this in your book. All right, so let's go over each one of those in terms of whether they share, because we didn't write that down. So first one, nonpolar covalent. You have this example of hydrogen. Both have one valence electron. It's much easier for them to just share that one valence electron with another hydrogen atom, and then they both have a stable electron configuration like helium. We call this a nonpolar covalent since both of these atoms are sharing the electron equally because they have similar attractions for that electron, similar electronegativities because they're the same atom. As a result, you don't end up with a charge on this. It says uncharged. We'll talk about that too. I like to show is this cute little picture of these two dogs here. We've got two chlorine dogs, and they are working with an electron or a bone, and they're sharing them equally, and they form chlorine. So we'll add to the table what's happening to the electrons. They're being shared equally, and as a result, Na, nothing is charged. Do you have jokes about covalent bonds? Do share. Just a little Kim Cat humor for you. Alright, next we have a polar covalent bond. And to demonstrate that, I have hydrogen fluoride. So you've got a hydrogen atom with one valence electron, a fluorine atom with 7 that could use one more. And what happens is the hydrogen and the fluorine share as they come close together. And because fluorine is more electronegative than hydrogen, it tends to hold on to that electron better. And so the electron is mostly with fluorine. So we call this an uneven sharing. It's not equal in terms of sharing. You have this picture over here where you've got chlorine hogging the electrons and hydrogen fighting for them. Chlorine's much stronger than hydrogen, and that's why the electrons are over there more often than they are with the hydrogen. And what results from this is you end up with a pole, well, we call it polar, a dipole. You end up with a positive end where the electron is not, and a negative end where the electron is more likely to hang out. And so, of course, here are the dogs again. Here you've got a stronger dog and a not so strong dog, and they're trying to share bones, but one's dog is stronger than the other, and so he has more of a portion of the bones than the other dog has. That's what we'd call polar covalent. They're still sharing, but one atom is holding on to those electrons more than the other. Okay, so we added this to the chart. That it is sharing but unequal, and that the result is two dipoles, a positive end and a negative end. Next, we'll talk about ionic bonds. And this is a cute little cartoon that says the name's bond, ionic bond, taken, not shared. And that's because the electrons are given and taken and not shared. So here's an example. Here you have sodium and chlorine. Sodium has one valence electron, chlorine has 7 and only needs one more. So sodium, to gain stability, loses that and gives it up completely to chlorine. Then they become charged. Sodium becomes positive, chlorine becomes negative, and now those are electrostatically attracted because they're opposite charges. So you see that transfer happening here between electrons. Here is the dogs as an example as well. Okay, so you have the two dogs fighting over the bones. One's so much stronger, the chlorine is so much stronger than the sodium that it completely rips away the bone or electron. And now they're electrostatically attracted because sodium's positive and chlorine is negative. Okay, we're going to add to our table. And that is what's happening to the electrons. Well, they're transferred. One gives, the other takes. And the result is you get a cation and an anion, a positively charged atom and a negatively charged atom. In case you were wondering, do metals combine together? Yes, they do. And when they do that, they form a metallic bond. And we'll talk later about metallic bonds in more detail. But if you want to see the dogs with them, it's like they're having a big party and they're just sharing bones and no one cares who's holding onto the bone. Alright, so what we're going to do next is we're going to look at a table of electronegativities and calculate the differences to figure out what type of bond. And so you have your own table of electronegativities on page 263 of your textbook. I'm going to use this one. Whatever worksheet you're using, use that one, or if you're using the book, use the one on page 263. So if we have Cl2, that means that we have 2 chlorine atoms. And so what we'll do is we will take chlorine, which is 3.0, and subtract chlorine, which is 3.0, and get a difference in electronegativity of 0. So that means anything less than 0.5 is a nonpolar covalent. And that's what happens, is you end up with something that's so similar in electronegativity or exactly the same that they just share, and they share equally. Next one is HCl. So we'll look up hydrogen, which is 2.1, and chlorine, which is 3.0. We'll take the bigger one, subtract the smaller one. So 3 minus 2.1 gives me an electronegativity difference of 0.9. And so on that table, 0.9 would be in the polar covalent range. Okay, then you have sodium chloride. Sodium is 0.9 and chlorine is 3.0. Take the bigger one minus the smaller one and get 2.1. And so anything greater than 1.7 is considered ionic, which we already know sodium chloride is ionic, but here's why. It's because sodium is a whole lot less electronegative than chlorine is, so it just completely gives its electron away to chlorine. Alright, that's it. Remember, like I said, please bring your questions tomorrow to class.